Stroke Occurrence and Recovery through TSI Velocity Part 1, number 1575. VPT 112, March 18, 2026. Gerald C. EclaireMD Foundation. Category: Stroke and Research Methodology. Preface: after finishing my presentation slides generation for a forthcoming medical conference on mortality disease risk using triggering sensitivity index TSI, including stroke approximately 85% metabolism-related, cardiovascular disease approximately 75%, and dementia approximately 55%. I began to think about extended but closely related medicine and science questions. I realized that a single TSI value measured at one instant, whether based on 3 biomarkers of glucose and 2 blood pressures, or averaged over a day, week, or month, is still essentially a snapshot, similar to traditional medical practice. To truly understand the original occurrence, development, and progression of various mortality diseases over time, I must examine their long-term trajectories. Like watching a continuous film instead of a single picture, this realization led me to introduce the concepts of velocity, speed of change, and change rate, degree of change over time of my developed TSI values. This paper analyzes 18 months of my TSI 3B velocity data, including 9 months before the stroke and 9 months after the stroke. Here, velocity is defined as c at time to minus TSI at time 1, divided by the time interval to minus 1. I apply both viscoplasticity and topology analyses, forming what I define as the VPT model, or the Viscoplastopology framework. Introduction: traditional medical analysis focuses on static measurements, such as biomarker values at a given moment. This snapshot approach is simple, but it fails to capture how a biological system actually behaves over time, particularly the long-term trajectory of disease origination, progression, and stage collapse. And interrelativance. A pathophysiological system is never static. It is dynamic, like a movie. It continuously accumulates stress and damage, releases energy, and undergoes partial recovery. These processes include reversibility, irreversibility, and mixed states. The system may change direction or trigger other conditions. Therefore, a statistics-based, linear, and still snapshot approach is not sufficient to fully understand the total pathophysiological picture of any patient. In this study, I extend my previously developed mortality diseases risk-triggering sensitivity index TSI by introducing its rate of change, defined as TSI velocity, or VTSI. This represents a fundamental shift from state TSI level to movement TSI velocity. This shift allows us to evaluate not only where the system is, but how it is moving and how it recovers over time. To further strengthen this framework, I integrate 4 methodologies into a unified biomedical system: 1 viscoplasticity VMT, energy accumulation and release; 2 topology TDA, trajectory and geometric structure change; 3 stochastic modeling, variability and fluctuations for TSI-based multiplicative dynamics, amplification, state, velocity, and recovery. Together, they form a complete nonlinear and dynamic system view, which I name the Viscoplastopology framework VPT. Conceptual framework. 1. Definition of TSI velocity. At TSI, I represent the earning system state at time step I. Since the time interval is constant monthly, velocity could be defined as VTSI equals TSI at plus 1, TSI in physics terms, TSI equals position, VTSI equals velocity. This simple transformation converts a static index into a dynamic system variable. 2. What is being measured? The key question becomes, how fast is the system returning to the safe zone? This represents a shift from where the system is to how the system behaves over time. Velocity captures direction, speed, and stability. 3. System meaning of velocity. Rate of change of TSI reflects system damping, recovery efficiency, stability, strength, interpedine, fast negative velocity, greater than strong recovery. Small changes, greater than stable adjustment. Large oscillations, then stable system behavior. This is the first time that recovery speed is directly quantified. 4. Multiplicative system behavior. Both disease development and recovery are not additive processes. They are multiplicative. Therefore, in their mathematical representation, multiplication is used instead of addition. Physiological variables interact: glucose, blood pressure, vascular condition, lifestyle behavior. Their combined effect is nonlinear. Small changes can amplify each other. Therefore, I define this framework as TSI-based multiplicative system dynamics. These emphasizes that system behavior arises from interaction, not simple summation. 5. Incremental accumulation recovery does not occur in one step. It happens through continuous small adjustments. This process is best described as incremental. Accumulations will improvements accumulate over time and gradually shift the system toward stability. 6. VMT energy integration using viscoplastic principles. TSI velocity strain interacts with three biomarker stressors: PP pulse pressure, SPP systolic blood pressure, EG average glucose. The strain is the TSI velocity, while TSI is defined as TSI equals SPP dBp at 45 SPP at 120 EG 120 120. This triple multiplicative interaction generates accumulated energy in a nonlinear, dynamic form, representing theta tail system load. The calculated VMT energy contribution ratios are PP at 36%, SPP at 33%, EG at 31%. This confirms that no single factor dominates. The system is governed by combined effects, which match most observed real-life biomedical conditions. 7. TDA trajectory analysis. A three-dimensional TDA trajectory is constructed with x-axis, TSI velocity, the output strain, y-axis, PP the dominant mechanical loading factor, z-axis, EG the fundamental metabolic factor. Multiple monthly data points form a continuous path in a topological space. This reveals system direction turning point structural transitions. These is not merely a collection of data points, it represents a real-life moving system. TSI velocities. TDA results 1. Pre-stroke phase, October 2024, June 2025. The system shows large velocity swings plus 8.92, minus 8, 74, minus 7, 78, plus 9.1 to high volatility repeated overshoot. This pre-stroke period from October 2024 through June 2, 2025 corresponds to an underdamped system with unstable oscillations. Two-dimensional radar charts with four variables show larger area size with imbalance across variables. Three-dimensional scattering trajectory shows widespread and irregular movement. This is a high-energy and stable state. 2. Stroke transition phase. July 2025. Key observations. Second TSI peak in June 2025. Largest negative velocity in July 2025, 12.46. Most important finding is that the stroke did not occur at the absolute maximum TSI. The highest TSI actually occurred in December 2024. However, the stroke occurred during a period of instability and rapid change over 6 to 7 months from December 2024 through June 2025. July 2025 represents a pivoting point, sharp trajectory turn, large energy release system reset behavior. July of 2025 is a transition point, not a peak point. 3. Immediate recovery phase. July of August 2025. The system shows strong negative velocity, 12.46, minus 5, 60 for rapid downward adjustment. This represents both high efficiency recovery phase and energy dissipation. The system is actively correcting itself. 4. Post-stroke stabilization. Sept 2025, March 2026. The system behavior changes significantly. Reduced velocity magnitude, smoother transition, smaller fluctuations. This corresponds to a more damped system SND and a controlled settling behavior with the following observations. 1. The cumulative VMT energy curve flattens. 2. The 3D TDA trajectory becomes compact. 3. The 2D radar chart becomes more balanced with a smaller area sizes. This indicates improved system stability. Amazingly, the traditional concept of the golden window of 3 months after stroke emerges naturally in this analysis results. Whether viewed through the viscoplastic energy VMT lens or the topological geometry TDA lens. Basic laws of physics truly apply to everything we observe in this world, including medicine. Medicine often lacks a quantitative, physics-based framework. Many phenomena, such as the 3-month stroke recovery window, can be better understood through system dynamics, energy behavior, and structural change. New concept: Recovery Velocity Index (RV). This study introduces Recovery Velocity Index (RVI). RVI measures how efficiently the system returns to the safe zone after disturbance. It represents recovery speed, system resilience, stability, efficiency. To biomedical systems from two different patients may have identical TSI values but very different RVI, one recovering quickly, one remaining unstable. RVI provides a new dimension for risk assessment in patients who have suffered stroke or heart attacks. Discussion. 1. Trajectory versus snapshot. A single value cannot describe system behavior. Two identical TSI values can represent recovery deterioration. Only trajectory and velocity can distinguish them. 2. Instability drives events. The key finding is, stroke is associated with instability, not peak value. This aligns with observations using engineering systems. Failure occurs during dynamic transition, not static maximum load. 3. Energy and structure together. Dynamic energy and geometric structure provide complementary views. Energy shows load accumulation, topology shows system evolution. Velocity connects both. 4. Recovery is a dynamic process. Recovery is not passive. It is an active process characterized by a damping controlled movement. Incremental accumulation system does not jump to stability. It settles into stability. 5. Complete system framework. The study establishes a unified framework. VMT greater than energetic greater than structure, stochastic variability C plus velocity minus greater than dynamic survey recovery behavior. This is a full dynamic system model. This is part 1.